Hi and welcome to, I think week 6 now. We're in week 6 and we're supposed to start a new chapter. And I sent you guys in, hold on, let me lower this thing. I sent you guys in a message regarding Java. I don't know if you have had a chance to look at it or not. I sent it just before class actually started. So I'm hoping that you guys have a chance to download it. It's not needed for today's lab, but it's going to be needed for next week's lab. And probably we'll need it down the road more. So we will need that for simulations. Okay, that's one thing. Also, I posted this week's lecture starting from today, and I also posted next week's lecture starting from Wednesday. Actually, this Wednesday it should be available for you guys. The quiz also covering chapters 24, 25, and 26 is also going to be available this coming Thursday after class. So if you want to look ahead, you can start it, but I recommend that you first of all cover all of the topics first. It's only, I think, like 20 some odd questions. And but you really need to make sure that you review everything and come in ready for the quiz. I know that the purpose of this quiz is, and I already stated what that purpose was. Of course, you're going to be earned grading for it, so it's going to be graded. But the purpose is actually to prepare you for the exam. The exam, I think I said by mistake, it's going to be the 12th, but it's going to be the 14th. Actually, it's a Wednesday. And I'm going to implement new changes to the way that we administered last time exam. And that is, I will try to make it available the night before the 14th. That means on the 13th in the evening, it should be available for you guys. This is to accommodate some people who probably would need to be at work, especially if they are working in some sort of a capacity that is required by law that they have to show up for work, so that they can work on their exam at night and then submit it. And then for those who basically are, they don't have that commitment, they can still come in the morning on Wednesday and submit their exam and work on it. The exam should not take more than an hour and a half to 2 hours, actually 2.5 hours. So I expect that people should have plenty of time now to go through it. The format is similar to exam 1. In a sense, it's going to be a take-home exam. So you will have access to all of the resources you need to basically complete your exam. Please do make sure, and of course I'm going to follow up this thing by another email, another message to everybody. Please make sure you review your submission after you submit it. Make sure that you open it and it's exactly what you want to see. For example, some of the people who submitted homework, by mistake, they submitted the wrong homework and they ended up getting no grade for that specific homework. So make sure that you submit everything the way it's supposed to be and look at it and all of that. So there should be plenty of time. So from Tuesday evening until noon, until basically 2:10 on that day, on Wednesday, you should have enough time to do everything in terms of the exam. So again, we will talk more about the exam and things like that. Any other questions? I know I graded everything that is supposed to be due, at least by the weekend of last week or Thursday of last week. So things related to grades, probably it's better to be discussed one-on-one, but things related to everything else, in general, that should be fine. It can be discussed in here. It's no problem. Any questions? And there is a lab today, okay? So we will meet later on in the lab around 2:30 after this class, okay? So if you guys don't have any questions and don't mind that, we can start with the topic. So I'm gonna share my screen with you guys. And let me find, first of all, what I need to share. Okay, so this is chapter 25 now. We are in week 6, and chapter 25 deals mainly with the resistors. So we introduced in chapter 24 the capacitor, which was a device that we need to use in electronic circuits. And where is my pen now? Yeah. And let me open a new tab in here. And let me draw. So this is what the symbol for the capacitor is. So if you see something like this in a circuit, that is a capacitor. Usually appended to it is its value. How many farads that is? 6 microfarads, 7 microfarads, 10 nanofarads, whatever the value, usually it's appended to it. If it's symbolic, you put the symbol on it, and that's it. C1, for example, for capacitor number 1. So this is an element of the circuit that we have discovered so far. That's the only thing. This portion is actually wires. And wires, by assumption, they have no resistance. We don't know what the resistance is, but we should be able to talk about it today. That's the topic of chapter 25, actually, is the resistors. So first of all, we need to define current. This is a new concept that we didn't have to deal with before, actually. We dealt with the charge, and we dealt mainly with the electric field. That's it. As a consequence of dealing with the electric field, we found another concept called the electrical potential. And the relationship between the potential and the electric field is that the potential yields an electric field, creates an electric field, if you wish. It doesn't create. It's the electric field derives. That's a word that is used. Derived from a potential. Okay, that's the word that we should probably be careful in using. So those are some of the concepts that we introduced so far. Today, we need to introduce, first of all, the concept of the current. And it's basically related to charges. I mean, charges in motion. That's what the current is. When charges move, that is what the current is. The rate at which the charge changes, that's basically what the definition of the current is. It's the derivative of Q with respect to time. Okay. So if Q is stationary, is not moving at all, so if the charges are not moving at all, the current is zero. That's it. Okay. If the charges are moving, then I have a finite current. Most of the times, though, what we're going to be dealing with is a steady current. And this word steady current is going to be critical later on when we deal with the chapter 20, what is it, 27? So the assumption then, not here yet, okay, is that the I is equal to a constant, as a matter of fact, meaning it's like a uniform motion when we were doing physics 4A. So basically, at some point, we're going to be dealing with the steady currents, but for right now, it doesn't matter. As long as I have a rate at which charge changes with respect to time, that is what I'm going to be calling current from now on. So we're going to define that. We'll talk about the resistivity, as we will see that we will have higher or lower current in a specific material, depending on a characteristic of that material, namely its resistivity. Its resistance in general. Resistance will depend on its geometry, but an intrinsic property of that material, namely, just like density. Density is an intrinsic property. For example, if the density is 7.874, that you know it's iron. Okay, how much mass you have of iron depending on how much volume, because the mass is equal to what is it? Density times volume. Same thing in here. Resistivity is specific to a specific element, okay, or a specific material, a specific compound for that matter. As long as now you have a material, now it has a resistivity depending on how it's structured, how it's chemically structured. How much resistance you have depends actually on the actual size of the object, okay? So that's the difference between the two, and we're going to talk about this too, okay? Resistance and resistivity. We're going to talk resistance specifically in conductors, okay? And then we'll introduce a new concept, and that is the battery, okay? The battery is characterized by a specific number, and that number is electromotive force. From the get-go, the word has force in it, but it's not a force. It's an energy, actually, okay? So I know the word is used, electromotive force, it may lead you to think that you're dealing with newtons, but as a matter of fact, you're dealing with volts, which is joules per coulomb, okay? So a battery, for example, that you go and buy from the store of 1.5 volts, that is its electromotive force, okay? So the electromotive force is how much energy is needed to move 1 coulomb, okay? That's basically what the electromotive, so it's a volt, okay? So that's basically what, so the word force in here may be, at least since you guys are coming off fresh from physics 4A, you may be tempted to think that it's some sort of a force or newtons or something like that. It's more of an energy than a force, okay? So that's one thing that we're going to be talking about. So we're building elements now. We have capacitors. Now we're going to add to them resistors, and then we're going to add to them batteries. So we have elements of circuits already. We have wires already. Just all we're missing right now is actually probably some few things, and we have a complete idea of what circuits. We're going to introduce immediately what switch is. Switch is an on and off, that's all, because we will need it for our experiments down the road. So a switch, like the button that you have in your house, you turn it on or off. That's it. So you have a circuit that has the line open or closed. Okay. So it has two characteristics that we're going to talk about them. Then how to calculate the resistance. We will see that the resistance is related to, the power first. Okay, the concept of power. Nothing matters in physics. It does not matter unless you talk energy. That's where the buck, that's where it matters really. That's how much you pay for it. Okay, so we have to talk in terms of the energy. We talked about the energy, if you guys remember, about the capacitor, that the energy inside the capacitor is proportional to the charge squared divided by 2c. Basically, it's equal to q squared over 2c. And in here, we'll find ourselves not dealing really with energy, but it's energy as is used per unit time, meaning power. Okay, so instead of dealing with it in terms of capacitor, which was joules, in here it's going to be in watts. That's the only difference between the two. So if you really care to know how much energy was consumed in a resistor, you will probably have to integrate. You have to sum from the initial time that you turn the switch, turn the switch on, till the time when the switch was probably open, in which case, basically, that's how much total energy was consumed. So remember, the relationship between power and energy is that power is just the derivative of the energy with respect to time. So that's something that you have seen in physics 4A. And we're going to build a model. This is not a real situation. Okay, we'll try to understand resistance in terms of classical mechanics, and it gives us an idea of what the resistance is. So that's basically, in a nutshell, chapter 25 for you guys. Okay, so this is a summary of chapter 25. So let's skip tab 2 because I want to come back to it later on after we build stuff right about here. Okay, or probably here. So we'll come back to it, but I want to talk about the resistors. So current, first of all. If you happen to go, for example, at night and look at the interstate, for example, 91, which is one of the worst freeways in the nation, actually, that I personally drive on, because it has usually heavy with traffic. It has a lot of cars. I mean, whichever direction you're going, east or west, toward the Riverside or toward the, Anaheim, it's really very bad. But if you happen to be on a lucky day, will you see only one car moving on the freeway? You know that's not traffic, is it? Traffic is more than a single car moving on the freeway. Same thing with the current. So a single charge moving in a circuit is really, by itself does not constitute a current. So current is a flow of charges over a long time. Okay, so the same thing with the traffic. It's this analogy for the current. So the current, by definition, if you like, okay, is the rate at which charges change with time. This is the first time we mentioned time in this class. Okay, technically all of the phenomenon up to this point, time was not included. Everything was given time for it to settle. Okay, so the transient behavior was not included at all. So we always wait until all the charges are in a specific position before we start calculating electric fields and things like that. And whether the superposition principle or anything else. So it requires that time is not a factor. Today, in a sense, it's also a factor, but because I'm going to assume at some point that we're dealing with steady current, so we're going to wait for the current actually to settle too. So we're going to be dealing with this current in terms of it settling, and in a sense also the time becomes irrelevant for this case too. We're not going to be dealing with it much, honestly. Okay. Now, in terms of units, the current is measured in amperes. This is the if you guys remember from your class of physics 4A, when they introduced units, they said that in the SI, le Système International, which is the meters, kilogram, second, the fourth element was the ampere. So it's MKSA, meters, kilogram, seconds, and ampere. This is the missing link all along since you started taking the sequence of calc-based courses. This is the ampere. This is as basic as the meter and kilogram in a second. So this is a fundamental unit. We've been dealing with the charges, and we were measuring them in coulombs, but that's not a fundamental unit. The fundamental unit, in fact, is the ampere. So if you're curious trying to find what is coulomb and an ampere are related to, use this expression. So a coulomb is an ampere second. So it's actually a derived unit. So coulomb, 1 coulomb, is 1 ampere that has accumulated over 1 second. So 1 coulomb was 1 ampere times a second. So that is, if you wish, the thing that we've been working so far, namely the coulomb charges, coulomb, and sometimes even the electric field, we said in Newton per meter, and we were using all kinds of things like that, but we said, wait a minute, this is, and the energy, for example, which was in joules, the volt has to do with a coulomb also, how many joules per coulomb. So we were dealing with a coulomb, but a coulomb actually, like I said, is a derived unit. This is as opposed to an ampere, which is a fundamental unit, which is a basic unit, okay? Just as much as the meter and the kilogram and the second, which were fundamental and basis by themselves, okay? Basic. So it's a fundamental unit, I should say, not basic, okay? Fundamental. Okay, so those are the in terms of units. So the ampere, which is a big current, by the way, if you look at the devices, you will see them a lot of the time labeled with ampere, and ampere by itself is a big current, okay? So you really don't want to have that running on your circuits unless you really have some heavy equipment, which may require more than an ampere, actually, a few amperes to do things. So that is one thing from the get-go. So the current is the rate at which, there's 2 R's in here sometimes, this thing doesn't write, is the rate at which charges change with time. So basically, if you have a place that has charges accumulating or basically disappearing, the rate at which that happens is the current. And the current, like I said, is measured in amperes. So that's basically in terms of the units and in terms of all of the fundamental things and things like that. Now, it would be interesting, and this is actually what Mr. Ohm did, okay, in the 1800s. He theorized the following. If I have a conductor, I'm going to draw a conductor as a cylinder, okay? This is a portion of a conductor because, of course, the charges, if they're moving through a conductor, you cannot move through a portion of it. You have to have basically a loop of some sort where there is a source of charges and the charges are moving, okay? This is a conductor. Okay? And I take a portion of the conductor, not the entire conductor, of length L. So this distance is L, okay? And cross section A, okay? And apply an electric field. I'm going to take the electric field pointing in this direction. So there is an electric field in this direction. Now remember, this is a conductor. It doesn't like electric fields to be present there. So the charges now start to move at will. Charges cannot stay stationary in a conductor because they are free to move. So the minute there is an electric field, they start to move. So these charges now, Q, are moving. And I'm not taking this fact that in practice, actually, the electrons that move, so they move in the opposite direction of the electric field. Remember, the force that causes them to move is QE. So if this Q is negative, then the direction of the force is opposite to the way that I drew the motion. Therefore, the charges, if they are electrons, and they are electrons, but put yourself in the early 1800s, the electron was not known. So basically, we're trying to build a model in here, and you will see down the road that the sign of Q doesn't matter, okay? That the result is independent of the sign of Q, okay? And we will ponder about that. That's actually the reason of the discussion today, is to find where the sign does not matter, okay? So we'll see when the sign doesn't matter, why the sign doesn't matter in this case. Okay, so we have an electric field. Remember, the electric field is always pointing from V high to V low. So this region must have a V high, and this region must have a V low. In other words, there is a difference in potential. And this difference in potential is expressed by that expression, okay? Oops. So if you remember from chapter 24, the difference in potential is equal to negative the integral between the 2 points of EDL, okay? And E is pointing from V high to V low. That's expected. I'm going to take DL also, which is integrated to give me my entire L just in the same direction. So that's basically the direction of motion of these charges. So the difference in potential then is going to be, remember, I'm going to take E to be uniform. So the electric field is uniform, which means it's constant, okay? So you're going to take it out of the integral, and E and DL point in the same direction, so their dot product is just their simple algebraic product. So this integral becomes minus E times L, because the L integrated from 0 to L is going to give me just the entire length of the wire. Obviously, the integration in here is the final value, which is V low, that is the last point, and this is V high. And this is as expected, minus V low minus V high is going to be V high minus V low. So this is the entire expression is going to be minus V high minus V low, which is expected to be minus EL. So in other words, the difference in potential is going to be just, which I'm going to label by V, by the way, instead of carrying this V low, V high. So this difference in potential, I'm going to call it V. So V is the potential between where the highest point is and the lowest point is in this portion. So V, instead of carrying this entire symbol with me, I'm going to just write the entire difference as just being V. For example, when you look at the power plug in your house, it says 120 volts. That's actually a difference in potential between the high and the low. So this is like equivalent of 120 volts. The difference between the high and the low is simply equal to EL, E times the electric field, okay? And this result, we saw a similar question when we were dealing, for example, with the parallel plates. So it's the same expression, except it was the D then, the distance separation between the plates. In this case, I took a wire. So it's the same situation where the electric field is assumed uniform. That's a key for this, doing this calculation. In other words, the electric current is uniform. So that's what I'm saying in here. So this time-dependent phenomenon is not included in the sense that we're saying that I is uniform. That's the key thing for this whole analysis. So the electric field is uniform. If it's not uniform, just integrate over the whole thing, okay? So that is an expression, which is important expression, relationship between the electric field and the electric potential in this wire. Now, Mr. Ohm, as I said, theorized the following, that if this electric field, what this electric field will do is going to create a current. So he was interested in the value of that current, how much current is going to flow through that. Before doing that, you note that if I have a big cross section, I will probably have bigger current because more charges will have room to run through, okay? If I have a narrower ending, I will have less current because then the same charges, they cannot squeeze as much because the rate at which it's going to be uniform. It's going to be uniform, therefore, so the area matters. So we have to define something, and that something is called the current density. So the current density in here is defined, J, as simply equal to the current over the area. So this is ampere per meter squared. So this is current density, and the unit for it is an ampere per meter squared. This way, then it doesn't matter what the cross section I have. If I have a small cross section or a big cross section, it doesn't matter. The whole analysis now should be cross section independent if I talk in terms of current densities. Remember, when we were doing charges, we have charge densities, we have linear distribution, area distribution over a specific area, and also over a volume. This one, no. This one only works on an area. So the current density is always an ampere per meter squared. There is no such a thing as an ampere per meter or an ampere per, unless you take a big slab where the width is already defined, okay? So it's always an ampere per meter squared. So this is a fundamental concept that is related to basically how much current is flowing per area per meter squared. That's where the analysis will be a little easier. So using the concept of the current density, Mr. Ampere said the following. Just like the cause and effect F equals to ma, if you guys remember from physics 4a, the effect in this case is the acceleration, which is the force over the inertia, okay? So the effect is this, and the cause is this one. What causes an acceleration to begin with is a force. The same thing in here. He argued that for conductors, the effect is the current density, and what causes this whole current to start in the conductor is the electric field to begin with, and divided by a property of the material, what's its inertia, okay? The equivalent of its inertia, which is called the resistivity in this case. So that's how Mr. Ohm's law is originally stated. So this is Ohm's law. I cannot really say it's a law, it's an approximation, because it may not hold for, first of all, non-conductors and other situations, and a law has to be absolute valid everywhere. So we call it loosely Ohm's law, okay? But it's known, especially in engineering, electrical engineering and electronics and everything else, as the law, fundamental law, basically, you start from, okay? So this is Ohm's law. So what this says then is that the current density, the current to be more specific, is the result of the electric field, okay? And materials will resist according to their own specific properties, okay? So, and this is similar to the mass, the inertia, and this is similar to the cause, which is the force, and this is the effect, which is the current density. So current density is the result of an electric field applied on a conductor, okay? As long as the electric field exists, there is a current density, there is a J, okay? So if E is 0, there is no current. On a conductor, okay, with resistivity rho. So the resistivity is the property of the object similar to the mass, okay? So the mass, which is the inertia of the object, which opposes a change in motion, this one opposes the current density, basically, the current in the circuit, to be more general, okay? So armed with these two expressions, so J is equal to E over rho. In some other literature, actually, 1 over rho is given a different name. Instead of just dividing 1 over rho, they use the symbol sigma. And the symbol sigma is actually not, which is called the conductivity. Conductivity is just 1 over the resistivity. So this is the conductivity, and conductivity is just the opposite or the inverse of the resistivity. So rho is the resistivity. That's what we're going to be sticking with, because that's going to be more involved in the calculation. So we have found from this argument that the current density, which is, by the way, I over A, based on this law of Mr. Ohm, is just the electric field over rho. Okay. In other words, from this expression, I already can find what the current is. Did I make a mistake in the expression here for the lower? Yeah, the lower rho, the higher J. Material with low resistivity, that means it's a good conductor. That means the current will be higher. A high resistivity, that means the current will be low. So that's the argument. So it's correct, okay? So based on this, let's look at the expression for E first. E is equal to V over E, or V over L, I'm sorry. Remember from the previous argument, we saw that V is equal to EL. The difference in potential is that expression. So I'm going to replace the value of E in here. And we're going to find an expression for V, the potential difference. Because the whole thing is, you're going to get a battery, you establish a potential difference, and you will see a current running through the whole thing. So I'm going to sub the value. So basically, this is where we're at. I over A is equal to E, which is V over L, and divided by rho. Rearrange this expression, and we can write it as V is equal to rho times L over A times the current. This is the expression for how the current and the voltage are related. We write it symbolically as V equal to Ri, okay? Where R for this material is equal to R is equal to rho times L over A, okay? I didn't mention what the units for rho are, but I'm going to mention what the units for R, for the resistance are. So R here is the resistance, okay? This is the resistance. And this is now another version of Ohm's law, because all we did was manipulate Ohm's law, basically, which is this expression, and we re-expressed the current density in terms of the current, and we expressed the electric field in terms of the electric potential, and we ended up with the relationship between the potential and the electric field, where all of these constants, namely the resistivity, the length of the wire now, the geometry of the wire really matters now, divided by the area A, which is also part of its geometry. So the geometry of the, just like when we do, for example, mass is equal to density times volume. Density by itself is an intrinsic property, but the mass itself is not. Same thing, that's in the expression, M depends on the size of the object. The mass depends on the size of the object. The resistance also depends on the size and the geometry of the object. That's in a similar fashion when we do the density experiments, for example, in, it doesn't matter what material, solids or liquids or gases or anything like that. So this is now the version that is more often called Ohm's law. This is not really the first, this is derived version of Ohm's law. But you will hear me, and you will see in lab instructions, and you will see in exams and problems, they talk about Ohm's law. Chances are, and I would say 95 to 99% chances are, that this is what they refer to, okay? V equal to Ri. Namely, there is a one-to-one in here relationship between the independent parameter and the dependent one. Usually you apply voltage and then you will see a current. But if you see a current, you know that the voltage is the one that caused it, okay? So I should be really expressed as V equal to R, to be more specific. In terms of units, okay? In terms of the units, V is measured in volts still, okay? I is measured in currents, which is amperes. I in amperes, okay? And volts, now we know what it is. It's coulomb per, basically per, what is it? I'm sorry, it's joules per coulomb, okay? And joules is you can break it down into a Newton times meter, and a Newton is a kilogram meter per second, and that's basically the force times meter, so it's going to be a kilogram meter squared per second squared. That's the joules divided by a coulomb, and a coulomb has to do with an ampere times second, so that's the volts is well defined in terms of everything, so the volts can be expressed. The current is an ampere, okay, so there is nothing you can do about it. Now, Ohm's law, the resistance R, you can express in terms of all of these units also combined. All you have to do is divide that expression by R, by the volt by an ampere, and it's going to be there. So it's a volt per ampere, okay? And the volt, as I said, is a kilogram meter squared divided by second squared divided by an ampere divided by a second, where one of these seconds is going to be, and then you have another second in here. So this is basically in terms of your units. It's going to be a kilogram meter squared divided by an ampere squared second cubed. Of course, we got sick and tired of calling it this many things. I mean, it's very long. So we gave it a name. And the name is in honor of Mr. Ohm, and we write capital omega. That is basically the unit for the resistance, okay? If you care to know its fundamental units, you can break it down into all of the fundamental units, and that's fine. But instead, we use the ohm, okay? And the symbol for it is capital omega. So from now on, that's basically the unit that we're going to be using. Now, in terms of resistivity, though, because of this relationship, this is ohms, this is meter squared. Cancel the meter squared with the meter, and you'll be left with a meter. So rho must be in ohm times meter. So the density, the resistivity, the unit for the resistivity is going to be in ohm meter. Okay, so that's in terms of all of the units for this things. Any questions so far? No. Can we continue then the discussion? You guys following? Okay, very good. So in terms of units, we have everything in here for this concept. So in terms of homework problems, though, what matters? This relationship matters a lot in this homework set. So you will need this one, and also you will need the one immediately above it. Okay. I don't think that we will need anything else so far. Okay. Anything else probably is not needed so far. Those are the two main things. Don't forget the units, okay? So those are the two main expressions that we will be dealing with. V equals to Ri, that is critical, and R equals to rho times L divided by A, where A is the cross-section of the wire, L is length. Of course, if I get a big wire, it's gonna have more resistance because the charges will have to move through the entire wire to get to the other end. The bigger the area, of course, the freer they can move, so they have more freedom, so the resistance is going to be less. If you narrow it, it's going to be more difficult for the charges to move. Okay, so that's basically what this expression. And rho is still a characteristic of the material. Now, it turns out a good conductor will have its rho very low, okay, of the order, as a matter of fact, of 10 to the negative 8. Okay. Ohm meter. A poor conductor or an insulator will have a value of 10 to the power 14 and even higher. See the scale of this resistivity? It's how many? It's 10 to the power 22 order of magnitude difference between a good conductor. This is a conductor, like copper, for example, and this is an insulator, like wood, for example. Okay, so that's the difference between them. So it doesn't matter what the cross section is. It doesn't matter what the length is. If it is wood, you're not going to run current through it. Charges will not move at all. So that's really in terms of the properties of the material. So this is the two types of materials that we have seen so far. Let me see where we stand in terms of this chapter right now. So we define the resistivity, calculate the conductor. So we already covered that part in here, okay? In terms of the, excuse me 1 second, let me clear my throat. We're going to come back to the explanation of this thing, so we have enough time to get back to it, because at this point, if I have to run a voltage difference, I need a source in here. I need something to do that, because a conductor by itself is neutral, doesn't have a charge in it. So when you go and buy a wire from Home Depot, like I said before, you're going to get a wire with charges, but the positive charge and the negative charges, they are equal. Okay, so it doesn't matter in this case what they do. Okay, so you're going to get the same amount of charges. So I really need something to push these charges, but the minute they end up on the other side, I need to collect them and bring them to the other side so that it stays neutral. Okay, and as long as there is this difference in potential, charges will fall. So I'm assuming in here the sign for them is positive, okay? Because at that time I didn't know what the sign is. Had they been electrons, which is the case, they will be falling from low to high. So the current actually, the charges will be moving from low to high, but it doesn't matter. I can think of those electrons as if they are positrons moving from high to low. It's the same thing, okay? So when you get a battery, which is really what that does to you, is establish that thing. It makes this possible. So let me get a battery in here and define what the battery is. First of all, this is the symbol for the battery. Okay, the long part. So it looks like a capacitor, but it has clearly two ends. One that is smaller, and sometimes they write it thicker. Okay, and this is longer. So this is your anode, and this is your cathode. Okay. So a battery has two terminals. So if you get a battery, let me see, what is my batteries in here? Do I have any? I think I do. Here is a battery from Amazon. Usually the sticking point in here, that is where the positive thing is. And sometimes they label it, okay? And the bottom one is where the negative is. So that's what I mean by it. So that's what the battery is. Battery usually has specific value associated with it. Most of the AA and the AAA are 1.5 volt. Okay, so what's going on in here? If I connect this to this device, which I'm going to call a resistor, by the way, the symbol for resistor is this. So I'm going to, since we already started this this point in here, let me do the symbol for the resistor. So it doesn't matter what makes it. This is the shape for the resistor. Okay. Again, those are two wires. This is part of the wire where you connect the resistor, and this is R. Okay. And it's going to be specific, 10 ohms, 100 ohms, 10,000 ohms, or 10 kilo ohms. So it doesn't matter. That's a specific value for the resistor. So this is, if you see an element like this one, that is what that is. So this is a resistor. And like the capacitor, okay, which has two bars, equals length. So, and that part of the wire where you connect it to, and that is basically what the specific symbol for it is C, okay? And again, that's microfarad or a nanofarad or a farad, doesn't matter. This one is in ohms. So that's the only two difference between these two. So if I have a resistor in my circuit and I want to push charges on it, okay? So I need the 1.5 volt. Remember, I'm taking positive charges moving this way. So the current will flow in this direction. Between you and I, we know what's going on actually. It's electrons moving in here. So the electrons themselves, they're moving in the opposite direction. So if I really have a microscope and look through and see what's going on, I see negative charges moving in the opposite direction, resulting in a positive current flowing in the opposite direction. Okay, so this is the same thing, okay? So let's say, for example, because negative charges, they would want to come to the positive side and end up in there because they see connection now. So they want to go and neutralize themselves. That's basically the basic fundamental idea behind it. Or if you wish, positive charges are moving to the negative side and want to sit there. So you have an electron, ends up on this side where it doesn't really belong because there are a bunch of positive charges in terms of the battery. So what the battery will do is it drags that charge, that negative charge, the electron, and place it on the opposite plate. Place it back in here. So in terms of the resistor, it is an inflow of charges and outflow of charges at all times. It stays neutral, so there is no problem with that, as long as the 1.5 volt works. And if you guys remember from way back when we did the electric potential, the energy U is equal to QV, okay? Except in the case of the battery, I'm not going to use the symbol V, I'm going to use the symbol epsilon, capital epsilon, big epsilon, okay? So what I'm saying in here is the following. This epsilon is the amount of energy per unit charge that is needed for the battery to operate. So the electromotive force, which is this concept in here, the electromotive force, as long as the battery still have juice in it, that's the word they use in the streets, juice, okay? It has an electromotive, it has energy, really. What is this? Sorry, okay. Did you guys hear this sound in here? Was it from my computer? No? It was ringing in my ear in here. Okay, I'm hearing things again, Sebastian. I'm sorry. I probably. Okay, so the electromotive force then is the energy required to move 1 coulomb. Basically, that's what it is by the battery. So it's an energy, so that we're clear on that. It's an energy. Oh man, why is this? So it's an energy per unit charge. Okay, so it's an energy, not a force. And I said that in the beginning, don't confuse the two, okay? So it's an energy per unit, it's volts, because an energy per unit charge is actually volts, okay? That's basically what this thing is. So, and again, you go to Walmart and you buy 1.5 volt battery, that is its electromotive force. If it sees a charge in the place it doesn't belong, it's going, so as long as it has that electromotive force, it's going to move it to the opposite side. End of the story, okay? So if the battery starts to degrade and at some point it drops to 1.3 volt, that's how much basically electromotive force is. So if the battery, for example, drops to 0.1, it's going to have hard any electromotive force at the end. So it's going to be useless for your circuit in there. It's going to drain, it's going to create nothing. So it's the time when you're going to replace it. So the electromotive force, and the symbol for it is epsilon, is the voltage specified for the battery, okay? So again, this is a new symbol now that we have to add to our circuit, which is the battery, okay? The battery now is made up with two ends, one longer than the other. The longer is always a positive, the shorter is always a negative. So if you see a battery connected this way, and if it's only a resistor on one side, it's going to have the current flowing from this side and coming to the other side. So that's basically what this battery is. So this is the 1.5 volt, and this is the 0 volt. Okay, so it's going to maintain that voltage difference between the ends in here. So the electric field inside the battery is pointing again always from positive to negative. Okay. But no charges can move there. It's only the battery that has chemical processes to force them to move. And they move against the electric field, basically. So if a negative charge ends up in here, that's what it's supposed to be. But the negative charge will fall in the negative region, which is against how the negative charges fall. If it's a positive charge and it ends up in here, it should stay there. But because this is a non-linear, non-electrical process, it's a chemical process, it's going to take this charge and puts it in the wrong place and move it against the electric field. So if it was only electrostatic forces, Q times E should put the charge in the place in there. But this is not electrostatic forces, okay? So these are non-electrostatic forces to move this one. They're usually chemical processes or other processes, for example, to force the charges where they need to be. Okay, and that is its power. Now, from this vantage point, now it's an electrostatic process. Here you have a positive plate. Here you have a negative plate. So there is a difference of potential V this way. So from here to here, we can use electricity. We can use the fact that E derives of a potential. E is equal to minus grad of V, which is electrostatics. We have no problem whatsoever from this end. This is perfectly fine. But inside and here, it's a black box that you don't understand and you don't care as long as it has that 1.5 volt, okay? It's not physics. It's not, I'm sorry, it's not, I should not say physics. It's not an electrostatic process, okay? That moves the charges against the way that they are supposed to be moving. So as long as you have that EMF, this is what it's called, okay? Electromotive force, the EMF, you're in good shape. The battery can operate. From now on, we're going to assume that all of our batteries are good. So if I tell you that the battery is 120 volt, that means it's still running good. That's running at 100%, 120 volt. So it's not draining whatsoever. Operationally, though, a battery has an internal resistance, so its voltage is slightly less than what it should be. So inside a real battery, a battery has its own resistance, and the actual voltage across its ends is not the EMF itself, but minus its R times I. So this is the voltage across the battery. Okay, this is in practice. Voltage of a battery. So if you think you bought 1.5 volt, you're actually getting slightly less than that because of the fact that the battery has an internal current, internal resistance. Now, if there is no current, if I is equal to 0, the battery should read exactly the EMF. But the minute the current starts to run in the circuit, the battery drops. Okay, and you will see that actually in the circuits when you do an actual lab. You have a battery, you have a power source battery, for example, 1.5 volts, meaning 3 volt. You measure its voltage and it reads 3 volts, okay, or very close from it. You connect the resistors and everything else, and the same voltmeter that was reading 3 volts will read less, okay? Because of the fact that it has an internal resistance. And internal resistance could be to the connections, could be to internal processes, because all of this has all kinds of process connections in here and there. So that's nature, okay? Most of the problems that we deal with in class are going to be the so-called ideal batteries, and ideal batteries are going to be where R is equal to 0, okay? If there is a problem, and I think there is one in the homework where R is not equal to 0, then you're going to deal with that, okay? You're going to just, this is how more realistic battery look like, okay? You connect, you have the battery itself plus its own internal resistor, and now the whole thing, you put them in a box, okay? So that's basically what that means. So this is the EMF, and this is the R, the internal resistor of the battery. So this is how it looks like. So it's in series with the battery. So whatever resistance you have connected to it, add to it the battery. Okay. So this is in terms of batteries and electromotive forces. We will come back there down the road for this concept more. Okay. In terms of the power, how much time? We still have time. Good time. In terms of power, which is something that we will need for this, because again, nothing matters unless unless we tally the energies. So imagine I have a voltage already, okay, which is Ri. Cross a resistor, R times I. This is Ohm's law. And I want to run through it another charge dq, okay? I want to find how much I need to spend for the next dq. That's going to cost me an energy, which is du, which is the potential times the charge. That's what we have seen. Q times the potential. But except now I have a dq that I'm going to add to it. So what I'm interested in then is the the power, which is by definition du over dt from physics 4a, and this will be simply v dq over dt, and dq over dt is simply the current, okay? That's what I have defined from the top to being the current. So the power in any circuit doesn't matter, resistor or no resistor, okay? You have a voltage difference. You would want to consume to see how much power is, and there is a current I, so this is the power. This is true all the time, always. In the case of the resistor though, V is equal to Ri, and I already have an I multiplying this, so in the case of a resistor, this is how much energy is being dissipated. So this is for a resistor though. So this is the power in a resistor. In general, the power is VI. In this specific case, it's R times I squared, okay? So again, this is in watts. You need to remember that this is in joules per second, not in joules, okay? So if you really are interested in finding the entire power and the entire energy, you have to integrate of some time limits, okay? And we will be dealing with that next chapter. We have to find what happened to the energy for a specific circuit, and we're going to be calculating the energy, knowing only the power, so we have to integrate, okay? So if the circuit is open for infinite amount of time, we have to sum it from 0 to infinity, from the time we turn the, we close the circuit to the time, to infinite amount of time. So basically to forever, okay? So this is in terms of the power. This is also another key relationship. Actually, both of them are, okay? This is true always. In the case of the resistor, this is expressed as Ri squared, okay? In terms of your house, basically connections and things like that, the power actually, what matters of all of your electronics and things like that, it's really because they are all equivalent to a resistor. So that's basically the expression that you will be dealing with, except that instead of dealing with the actual current, which is time varying current, because we deal with AC currents actually in houses, we deal with the so-called effective current, which is involve a square root of 2 in the expression. We'll get into that when we deal with the AC currents, okay? Let's try to explain what these things are. So far, we have a lot of elements in the circuit. We have batteries, we have resistors, we have capacitors. We have built quite a bit of a dictionary in terms of things. Okay, I'm going to add to them just another thing in here for the case of the circuits that we will be needing, namely the switch. Switch is characterized by basically this on and off position. So this is a switch. Okay, so this switch, you can close it, and now it becomes a wire. When you close it, the resistance, so right now the resistance is an infinite because it's open. But when you close it, the resistance drops to 0. So it has two values, 0 or infinite. This is one of the types of the switches. You might looking at also another kind of switch, the so-called AB switch. An AB switch is basically three-way switch. So you have, it connects to either this side or that side, okay? So depending on which way you turn it. And actually in the lab, we have an AB switches, okay? So that's the some of the switches. So this is another kind of a switch also. But most of the time, most of the class actually will be dealing with just the singles switch structure. So this is a dictionary we have. We have batteries, we have resistors, we have capacitors, and we just discovered also the switch. Okay, so that's what we have seen so far. Let's try to explain resistance, okay, because that's kind of something that we need to understand what's going on. We have about half an hour, no, actually 25 minutes to do that. So we're going to go back to our initial schematic and promise you that the Q doesn't matter. So this is where it we will see that. The sign of Q doesn't matter. So again, this is a wire of length L. And I said that for this material, it's made up of charges, okay? These are the charges, and they are moving. Each one of these charges has a value Q, and they are moving more or less in the same direction in here. On average, they're moving with a drift velocity, which I'm going to call VD, okay? So that's the drift velocity. So the current, again, is just the ratio of the number of charges per unit time, that flow per unit time. Since they are drifting with an average velocity, so this is an average. On average, inside an electric field, of course, I'm assuming that there is an E in here of some sort, okay? And since it's a uniform velocity, uniform current, I mean steady current, that means this VD is more or less uniform. It's a constant number with which everything is flowing. So if there is some time-dependent behavior, we'll wait for it to settle, and then we will go through these charges and find how much they are moving. So I'm going to take a cross-section again, A, here is A, and wait 1 second and see how many charges went by. That is the reasoning that I'm going to use. For that, I'm going to assume my material has N charges, charge carriers, I should say, charge carriers, because at that time we didn't know that they were electrons, okay? N charge carriers per unit volume. How many charges do you have, depending, for example, on the outer shell of the atom? Is it 2, 3, and then you're going to find the density of the material and multiply it by that number, and that's it. That's a specific number. It's usually a fixed number, okay? Depends on the actual density of the material. So that's the number of charge carriers per unit volume. Now, I have N charges. Each one of them is carrying Q charge. So Q is the charge of the charge carriers. Okay? M is their mass. If it's an electron, we know exactly what the mass of the electron is. If it's the electron, we know exactly what the charge of the electron is. So these are not, so this is the mass of the charge carriers. So we have everything for this situation here. Now, I have a cross section A, and I wait 1 second. After 1 second, this charge is drafting with the velocity Vd. So the charges that were in here, they would have traveled the distance Vd. Vd times 1 second, if you care to find it, okay? So this is basically the volume that I need to find the number of charges that flew in 1 second. So after dt amount of time, it's Vd times dt is the length of this distance, okay? So the charges then, or the current to be more specific, is the number of charges per second. The current is the number of charges, which remember I have N per unit volume. And the volume is area times length. Area times length. And the length is Vd times dt, or Vd per second. So this is the number of the charges per second times the charge of each and every one of them. Because if I have 1 billion, each one of them is carrying Q, so I have 1 billion Q coulombs. Okay? Per second, because this whole event is happening per second. So that's basically the expression of the current in terms of the charge density, or the charge carrier density, in terms of the cross section of the wire, in terms of the drift velocity, because they're moving in uniform motion, and in terms of Q, their unique charges. So this is an expression for my current. Now the only problem is trying to find what this Vd is, the drift velocity. Remember, each charge has a mass m. And each charge, if I don't apply an electric field, is moving at random, moving every which way. So the charges, if there is no electric field, they're moving, each and every one of them. The index I is for their average, for their individual velocities. One of them could be going this way, the other one going that way. They're random. So this is random motion. This is in the absence of the electric field. E is equal to 0. Okay? But when the electric field is applied, they more or less move in the same direction now. Okay? So if I apply F equals to ma for each and every one of these charges, I find that they accelerate A, which is force divided by mass. Each one of them is carrying same mass, which is m. Each one of them has the same charge Q, and each one of them is subject to the same force. So each one of them will have an acceleration, which is Q, AI equals to Q, which is their charge, times the electric field divided by the mass, which are all the same. But now, if I want to integrate this expression to find the velocity of each one of them, it's going to be VI, which is this time, this expression times time. So it's going to be QE over M times time plus the initial velocity. Remember, each and every one of them has a random motion by itself, and the random motion in the absence of the electric field. Okay? Obviously, the average of the random motion, if I average this expression, is going to be 0 because motion is happening every way. So this is on average is 0. But each one of them has a specific velocity on by itself. But when I average it overall, there is no current in a wire sitting by itself. Okay, so if I pick up any metal, for example, this one, it has no current by itself. Otherwise, if the electrons somehow start moving in one way or the other by themselves with no external field, then I will have a current, and that is not the case. So on average, they have a 0 velocity. But when definitely I apply an electric field, they will have an average velocity. So I am going to average this last expression and call it the drift velocity. So the drift velocity with which all the charges will move is the average of all of these expressions now due to the electric field. So it's going to be the average of this expression. Q is constant, E is constant, and M is constant. And the average time, the time T is the time between successive collisions. So basically I have an electron in here and it's subject, it was moving at random, okay? Or charge moving at random. You apply to it an electric field and it starts to move based on this expression. Then bang, it hits something else and stops and goes in every which way direction. It forgets what it was doing, okay? And then it accelerates again because of the electric field, and then it hits another obstacle. The time between successive collisions, I'm going to call it on average tau. So this is the average time between the different collisions. Some charges, they will get into collision immediately. Some of them will take a long time before getting into collisions, but the average time between successive collisions is my tau, plus the average of this random velocities, which is 0. So the drift velocity then is related to the charge carriers times E divided by the mass of the charge carriers times the average time between collisions. Okay, so that as long as that time is long enough for the charge to gain enough velocity, so they will start drifting. If that average time is short, then they would not have any, hardly basically any, the electric field would not have any effect whatsoever on these charge carriers. So let's summarize this expression here for VD that we found with the expression for the current that I already have found. So I'm going to sub the value of VD in here, which is the Q times E divided by mass times tau. And now we have an expression for the electric current. I is equal to N times the area times VD, and VD I already found it. So this is VD, which is QE divided by M times tau. So this is QE divided by M times tau times another Q times this Q. Okay, that is because I needed the charges themselves to find how many charges move per second. So this is the Q there, because this is just the number of charges times Q. That is give me the number of charges per unit second, because this is the number of charges per second. So now times another Q, that's where the Q squared is going to come into play. So first of all, the current density J, okay, which is just I over A, that means A cancels, is equal to N times Q squared divided times tau divided by M times E. Contrast that with the expression of Mr. Ohm that says basically that J is equal to E over rho. That gives me an explanation of what rho is. So rho is M divided by N times Q squared times tau. So the resistivity then must be the mass of the charge carriers divided by their number per unit volume times the carrier charge squared times tau, okay? Times tau, the average time between collisions. So let's think about this expression for a moment. M is the mass of the charge carriers. We know today that they are electrons. Okay, so M is fixed, 10 to the negative 31 kilograms. N is a property of the material. It has to do with the density, which is most of the time fixed too. You don't really have a lot of control over it. Okay. N is just has to do with the density, and it's usually varies very little between a material and material. For example, between iron and what is it, a less dense material, like for example aluminum, is a very small number. Both of them are good carriers, by the way, good conductors. I'm sorry. Okay. An insulator, for example, take any material, it's not going to be too far from these numbers. Actually, it's only probably an order of magnitude different, but that should not really make it 10 to the power 22 order of magnitude. So that doesn't explain that. Q is fixed too. We know it's the charge of the electrons. This is why it doesn't matter the sign. Remember, I was putting the charge, the current this way or the other way. It doesn't matter because the resistivity has Q squared in it. So if it was negative, negative times negative is going to be positive. So this is the answer to the prompt that I said in the beginning. Why the sign doesn't matter? It doesn't matter because at the end, positive charge is moving from the positive plate to the negative plate. I mean, for the negative end, or the anode to the cathode in the actual circuit, or negative charges moving in the opposite direction, it's the same effect in terms of mathematically, at least. Okay, symbolically, it's also the same thing. What really matters really in this whole expression is tau, the average time between collisions. That's the one that makes the difference between a 10 to the negative 8 good conductor and 10 to the power 14 ohm per meter, ohm meter per conductor or an insulator. That time, the average time. If the charge carrier, the electrons, for example, they want to accelerate and immediately hit an obstacle, like for example, another ion, which is most of the time is, they hit the atom, they cannot go anywhere, and then they stick, and then they stick. They cannot go anywhere. So this is really the difference between a good conductor and a bad conductor, is that tau. Okay, this is what makes a difference. The longer this time, the less is rho, the good the conductor is. The shorter this time, the higher rho is, and the poorer is the conductor is. Obviously, if somehow we invent a new charge carriers with less mass, with M is less, then in this case, the rho will be less. So we'll have a better conductor. Okay? But like I said, we don't have really good, that means it's inertia. The mass, actual mass, is low. Okay? Which is also another connection between Ohm's law and also F equals to ma. Rho and M are proportional. The actual physical inertia from physics 4a and this type of resistance are actually proportional. That gives you actually an indication that Mr. Ohm was actually in a good track. Okay, so although, like I said in the beginning, this is not an exact law to be applied everywhere, it's an approximation, but actually there's a connection between the two, except that this rho now has a bunch of other things too. Okay, if you have more charges available per unit volume, namely n is higher, then of course rho also is going to be smaller. Of course, if the charge carriers can carry more charges with them while they're moving with less mass, of course you'll have higher current. So the more Q is, so that's what this expression means. But all of those are basically set aside. The biggest factor in this expression is rho, is tau itself. Tau, which is TAU. I sometimes looks like it's a W, but it's not a W. It's TAU, tau. Okay, and I think you used this symbol when you did the torque and way back when we were doing physics 4a. Okay, it's the same symbol, and we're going to need it actually next chapter, and we're going to call it something else. We're going to have a different use for it, and we call it different tau. Tau usually is reserved for time. Okay, so this is in this case, and this is the only case you're going to see it actually. So don't be bugged too much with it, because we're not going to be spending too much time on this in terms of applications, because actually this phenomenon is not really classical mechanics. That's why I'm saying it's a model, because it's actually more related to the realms of quantum mechanics. And most of the research and the work, if you're trying to build a specific conductor with specific properties, trying to get a specific resistivity, this is where the work is. Most of the time has to do with the time between, the average time between collisions. So this is the average time between collisions. So it's in seconds. Okay. The longer this average time, the better the conductor is. The shorter this time is, the poorer the conductor is. Okay. So that's how you can interpret it. Okay. So this is in a nutshell, this chapter. Okay. And I have actually the publisher from the website. They sent me the wrong printed copy. They sent me the 15th edition printed copy, but from the website, I have access to the 14th edition. So this is how the chapter looks like. Okay. And we should be able to do our lab. Next Wednesday when we meet, we're going to probably briefly discuss these things. And we're going to do maybe some brief applications, but we're going to move to chapter 26. That's why it's available for you guys on Wednesday. Okay. Because I want to get the theory as much as possible out of the way. And then next Monday, we will have lab. And the Monday after will be reserved to the review. Actually, we'll do the review for the first session. We'll just go through basically the problems from the homework. All the homework problems are due on October 10th, meaning before the exam. So please do them all. They should be very helpful for you to preparing exam 2. Okay. And also when you do them, I know that you have resources, some of you do, where you can find the solutions. You have to understand what the solutions mean and you have to explain them and see if you expand to them and see if you can basically different variations of them. Let's say, for example, instead of having 2 capacitors, you have 3 or a single capacitors. Do 2 capacitors behave the same way? For example, if you have a single one of them in a different configuration and so on and so forth, or the same thing with the resistors, or you change, for example, the voltage to see if the voltage, did it make sense in terms of your voltage? Do you have more voltage than when you started with, or you are in good? So that's basically the type of the discussions I'm looking for to show really that you understand what you have seen in terms of solutions from other sources. So I need to make sure that you're understanding these things. So that should be due by October 10th. The quiz is due by October 12th, which is the last day of doing reviews, basically. Then October 13th, hopefully you're finishing your reviews, and then in the evening, like I said, you should have your open book exam 2. Okay, it should be due on October 14th. October 14th, there will be no live session. Okay. So the only thing that I will be answering is any questions that you should have. Hopefully you have it by evening on the 13th. If there is any problems, like last problem, I think there was a 10 to the negative 6 instead of, it should be 10 to the negative 6 for a micro something, micro coulomb, and I put it 10 to the positive 6, although I had it somewhere else covered, but there was another issue which I forgot what it was. So if there are any issues related to the exam this way, please communicate them to me as soon as possible, and I'll post them on Canvas, basically sending a message to everybody, taking notes of the fact that these things should be fixed there, and hopefully you don't have any problems. Okay, do you have any questions for me? If not, the lab instructions for this lab, today's lab, which is the, I already forgot, it's the resistance, it's today's topic, I'm sorry, is going to be in about half an hour. So I'll see you there. Good? Yes or no? Okay, very good. Thank you, Heather. Thank you, Daniel. I'll see you guys, okay? Bye.